All right. So another program. That first year of teaching, I was just gung-ho. And, nobody told me what to teach. So I just taught things. And this is another program that I got them to write. And I think it's great. And then years later, some student asked me if I could give him a summer project. And I got him to code this up. So I think it's still out there, but the user interface isn't very good. All right, so what is the problem? Is you're given these two pictures, and this arrow in here tells me you put your fingers here. If you grab an object, a two-dimensional picture with two fingers, then you can rotate it by moving these fingers, and you can make it bigger and smaller by moving these two fingers, right? So this recursion play, I'll tell you where the fingers go for a picture, and then the recursion tells me how to rotate and shrink the picture to put it somewhere else. All right? So if n equals 0, it draws the base case picture. If n equals 1, it draws the square picture, and then it takes the n equals 0 picture and kind of rotates it and shrinks it and puts it in place. All right? So that's n equals 2 picture, n equals 1 picture. So memorize the n equals 1 picture. What's the n equals 2 picture is the square with the n equals 1 picture rotated and shrunk. All right? And what's the n equals 3 is you draw the n equals 2 inside. Right? And what's n equals 30? It's pretty. Right? Isn't that great? So that program, yeah, somebody play with it. Go online and find it. All right, see if it's still working. It's been a number of years since anybody's talked to me about it. So nature is beautiful too, right? Let's get all inspired by nature. This is a leaf. And how do we draw it? Well, the base case will be nothing. And the recursive picture has a stem, and then it recurses a number of times. Right? So what's the n equals 1 case is just a stem with nothing to recurse. Right? So that's going to be just a little stem. And then n equals 2 is going to be a stem with the 1 lines on it. Right? And n equals 3, and n equals 4, n equals 5. Right? People see that? No? Yes? Right? What is an n equals 5? Right? If you agree that this is an n equals 4, then what is n equals 5? It's the stem with little, then we take the n equals 4 and we rotate it and shrink it and put 1 there and 1 there and 1 there and 1 there. Right? So these are all n equals 4s. Right? And what's an n equals 4? It's a stem with little n equals 3s hanging off of it. Right? Does that make sense? Now, I don't know how nature works, but surely it's doing something like this. Right? I mean, it looks like this, so what else could it be doing? I don't know. Everybody buy this one? All right, so here's another one that you've probably seen. The base case is a line, and the recursive case takes the previous picture and shrinks it by a factor of 3 so that it's going from here down to here, and then it puts 4 copies of it around. Right? And so so n equals 0 is a line, but then n equals 1, you take every line and you replace it with these pictures, right? So, well, I mean, here's a little copy of an n equals 1, right? And there's a slightly bigger copy of n equals 2, and a bigger copy of n equals 3, and 4, and 5, right? So you can see what is the 5. This is a 4, and over there's a 4, and over there's a 4, and over there's a 4. Right? Does that make sense? And that's a fractal. And one of the things that makes a fractal is that they can be infinitely long. So it's like if this is a coastline, if you take a ruler that's this big and you measure the coastline, you'll get one answer. But if you take a smaller ruler, you're going to get a longer answer for the length of the coast, right? So let's calculate the length of this line. Well, the length of the line when you recurse n times is, well, what is it? Well, you take the length if you're in recurse n minus 1 time, and you shrink it down by a factor of 3. And then you get 4 of them, right? So that's, everybody got that recurrence relation? Right? And then if you keep going, right, it grows exponentially with the number of levels. And if you go to infinity, then it becomes infinitely long. Right? So here's one question. Suppose I drew right here, I don't know, what was this, n equals 5? Suppose I drew n equals 6 or 7 or 8 or 9 or 10. How would the picture look different? Right, it's going to have a little finer detail in here, but the pixels aren't big enough to pick them up, so it would actually look exactly the same. Right, people follow that? So here's another thing I got them to do in first year is to make a maze like this. Right? So here are all these little rooms, and there's little doors. So how did we do rooms? Well, I'm given the room with a door in the one corner. Right? That's sort of the precondition. And what do is I randomly choose a spot somewhere in the room, and I create walls, and I create doors here and here. Right? Now, each of these is a room with a couple, at least one door, 2 doors. And so then how do we fill those in? How do you fill in each of those rooms? No, because that's micromanaging your friends. The way you do it is you have friends do it. Right? But she's right. That's what our friends will do. Right? Everybody follow that? And they fill in the rest. And another parameter that it had was each guy either knows that he has cheese or he doesn't have cheese. Right? So that's an extra parameter up there. And then if we have cheese, we choose one of our friends to have cheese and the others don't have cheese. And that effectively puts the cheese in a random room. Right? And what's the base case is when the room's too small to divide it. All right, and the next topic we're going to be covering, starting after the test, I guess, will be how to find the cheese in a maze.